Hello. Hello. Yeah, hi. Sure. Yeah, sure, ma'am.
Good afternoon, everyone. I welcome you all to our daily session, Data-Driven Innovation in AI, from CPU cores to GPU threads and beyond. I am Anshul Gupta from third year CMPL. Today we have a very special guest with us, Mr. Prasanna Biswas. He was in our 2018 CMPN batch. Currently, he is working as the advisory research engineer at IBM India Research Lab. Previously, he has also worked at companies like Intel and Qualcomm. We are very happy to have you with us. Thank you for taking the time for taking this session. Please take over the session, sir.
Okay, sure. And thanks a lot. Thanks a lot for. First of all, I'm really excited to be here. And for the folks, thank you for attending the lecture. And I'm really excited to be here because this is the institute from where I did my bachelor's. And coming here again as a guest lecture, like seems grateful. And yeah, I feel grateful about it. And for that, I would like to thank Nupur ma'am, Indu ma'am, Priya ma'am, Gresha ma'am for giving me this opportunity, and also to Achal and Sudarshan for coordinating the session. And yeah, so let's start. I will be sharing my screen, and any one of you, just let me know if my screen is visible. Okay. And first of all, am I audible to all?
Yes, you are audible and the screen is also visible.
Okay, sure. So just a second. Yeah, let's start. Okay, so first of all, the session is about hardware-driven innovation in artificial intelligence. Okay, so currently we see a trend wherein kind of very less people. Okay. So first of all, just a quick show of hands. Like, how many of you have ever thought what happens beneath your Python or PyTorch program? What exactly happens on the CPU and the GPU? Okay. Okay, I guess here it might not be visible because like it's a room kind of a setting. Like going through the CPU and the GPU programming and see how the speed up is there from CPU to GPU. And in the meantime, we'll learn more about the accelerators as well. So here it's a brief agenda. So first I'll just tell you about myself, what I exactly work on and what all things we did, and then we will just take a look at why hardware matters in artificial intelligence. Then we will just take a look at the two prominent architectures, CPU and GPU, and we will also see why CPU are the perfect fit for the graphics. Okay, and then we will see how AI systems are built using CPU and GPU, CPU as a host and GPU as a device. And then we have a demo wherein we will go through the code of the CPU and GPU. Okay, so for GPU, we will use the Triton language to program the GPU and see how much is the speed up from CPU to GPU. Then we will have modes. Okay, then we will just study about PyTorch and a bit of a PyTorch and why PyTorch, and also we will study about the two modes, which is eager mode and compile mode, and then we'll just take a look at how PyTorch compile mode leverages the hardware capabilities. And then we again have a demo wherein I'll just walk you through the code step by step, and we will see how compile mode speed up over the PyTorch default mode. And then I will give you a brief introduction of the ML accelerators, and then any questions. Okay, then we'll take the questions, or we can take the questions in mid as well after CPU or GPU performance. Okay, so about me. So as Achal introduced, I am working as an advisory research engineer at IBM India Research Lab. So my job now, right now, is to work on the IBM Spyre software stack, wherein I'm working for this PyTorch backend. And I have a 5 years of experience for optimizing ML models for different hardware accelerators. For example, in 2020, I was working with Qualcomm, wherein I was working with this AI 100 chip. Okay, and here I will just show you this thing. So when we were working with Qualcomm, right? So at around 2023, we published this paper which uses graph networks to optimize the compiler. And yeah, it was very good to see that it was being referenced by this National Library of Medicine, the American agency. So to use this for their thing like the protein or something of that sort. Yeah, so we were doing that kind of a thing there. And during my Intel days, we published two research papers, which was handwriting generation. And recently I joined IBM Research Lab, wherein I'm working for developing the PyTorch stack. Okay, so here, like coming to this slide. So this is where I want you guys to pay attention on. So why hardware matters in AI. So this is a small snippet from like I've taken it from Economic Times. Okay, so wherein this guy Sam Altman. Okay, so you all might know about the Sam Altman. He is CEO of OpenAI. So in a podcast with his brother Jack Altman, Sam said, right? Just a second, I'll just take this laser pen. Yeah. So here he said that this current hardware is not able to keep up with the changing and increasing AI demands. Okay. And why he said that, I'll just explain you through these two diagrams. Okay. Just pay a bit attention here. So here, if you see the transformer size, okay, so the transformer size has increased 410 times in last 2 years. So for example, from the place, okay, where this transformer model came into picture, like the paper by Vaswani, which is the paper title Attention Is All You Need, from there the transformer came into existence. From there to say GPT-3 or Megatron, okay, so every 2 years the transformer size is increasing drastically. Okay. But if you see the memory size of GPUs, for example, initially Nvidia, when Nvidia was publishing like making the GPUs, so they had this different architectures, right? So they have this P100, which is a Pascal architecture, then V100 Voltas architecture, then A100, which is Ampere, and H is Hopper. Recently they are working on the Blackwell architectures as well, but here's still the Hopper one. Okay, so here if you see, the memory increases 2x every 2 years. Okay, and the flop is also somewhere around 3x every 2 years. But the transformer size, or the parameters inside the transformer or the ML models is increasing in a very rapid space. Also, if you see here the hardware flops, it is get like it has increased 60,000 times in 20 years. But if you roughly think it, it is just the 3x every 2 years. Okay. And here also the DRAM bandwidth, it's 1.66 every 2 years. Interconnect bandwidth is 1.4x every 2 years. So what's the flop? Flop is floating point operations per second. How many floating point operations you can do on your hardware per second is the flops. And here DRAM bandwidth is, so say here is the memory size of the GPU, which is 80 GB. So 80 GB is the size of the RAM of the GPU. But what's the bandwidth, like how fast you can access the data from the RAM? It's the DRAM bandwidth. And this interconnect bandwidth is the PCIe bus or the NVLink, which you use to connect CPU to GPU, or two GPUs, like the connection between the two GPUs. Okay. So here from these two graphs you might understand that the hardware are growing, the hardware and the hardware flops are growing steadily. They are growing, but they are growing steadily. But suddenly, due to this increasing AI demands and ML workloads, so the models have been scaling very rapidly. Okay. And the hardwares are not able to cope up with that scenario. So that's where hardware aware information comes into play. For example, if you want to run a model, okay, in a hardware in an optimized way, and since you have a limited amount of resources inside a hardware, how you can optimize the model for running efficiently on the hardware is something we need to look at. Okay. um, I hope, am I audible still, right?
Yes, you are audible.
Okay.
Just a small thing. Can you just put your presentation to full screen so that it's visible more clearly?
Okay, sure. Yeah, actually I'm connected to an extended desktop, that's why. Just a second, I'll just check whether I can just zoom this a bit here only. Okay. Yeah, yeah. Second. Okay. Is it okay now?
Yeah, it's better.
Okay,
Thank you.
fine. Yeah, sure, sure. Works. Okay, so this is the thing. And yeah, okay, so this is why I was like I have kept this slide, just so you guys can appreciate why this optimization on hardware is required. Because AI model, I'll just repeat it again, because AI model are scaling very rapidly compared to the developments on the hardware. Okay. So this is the brief overview why we are taking this lecture. Okay. So we'll just start about with the two prominent architectures, which is CPU and GPU. Okay. So as you see from this picture, so this is the implementation, the picture. And here you see, so the CPU is a latency oriented approach, the GPU is a throughput oriented approach. And what is that, we'll see. So here you see on in the CPU, right? In the CPU you have limited number of cores. For example, this is a quad core CPU, you have 8 cores, and then for each core you have a certain amount of control cache. You have L1 cache, you have L2 cache, L3 cache, and DRAM. Okay, so if you see, this architecture is designed to reduce the latency of a program. For example, if you so L2 cache is most frequently used inside a program. Okay, then the one which is less frequently used is in L2 cache, then L3 cache, and then DRAM. So this is how the hierarchical approach is maintained, so that the memory access latency is reduced dramatically. And then you have a sophisticated control cache. The control cache is bigger in the CPU scenario, and it is used to branch prediction kind of thing is there. So if you are like say if your program has if else thing, okay, so which branch you will be taking and what data to fetch from that branch, so these are being done by the control cache. So this is a very sophisticated architecture, and many sophisticated programs like which requires mainly the branching or the conditions or execution of the program in a latency oriented manner uses CPU. Okay, so the CPU is really the good architecture for running anything, for running any program. Okay, and what the GPU is about, if you see the GPU, it's all green. Okay, it's all green, it's all about the cores, massive number of cores with very small control cache and very small L1 cache. Very small control cache means the branch prediction kind of thing is not there. The instruction cache is very small. So that's where you might have heard about this SIMT programming language or SIMD programming language, which is single instruction multiple thread or single instruction multiple data. Because say these individual cores, they don't have their own control cache or say instruction cache. So what happens is you just issue one instruction and all these cores follow the same instruction. So it works massive, like it works on the massive data. You just give one instruction and it will just do the computation of the on the massive amount of data. For example, the better example can be matrix multiplication, wherein the instruction is very small, it's just the matrix multiply. Okay, it's just the one instruction, but there are say 1000 into like 1000 cross 1000 matrix of A, 1000 cross 1000 matrix of B. So the number of computation will be order of n cube, which is order of 10 cube, like 10 power 9 number of computation will be there. So massive computation with a single instruction. So this is where GPU comes into play. So GPU has very limited amount of control cache, very limited amount of L1 cache, and very limited amount of things to reduce the latency. Okay, so what it does, it hides the latency. It has to take the data from L2 cache. Okay, it cannot take the data from L1 or L2 because those are very small. So it has to go to L2. Okay, and if the L2 is not there, it has to go to DRAM. So there's the latency thing for fetching the data, and that latency is covered by the massive computation or the massive raw power the GPU have. So here, for example, in a very brief overview, you can think of, if you have one single task, CPU is the best suited for it. And this also you can experiment while running the code. If you have just one single task, CPU will perform way better than GPU. Okay, so say for one task, for one particular task, CPU is the best. And say if you want to do massively parallel task, okay, some like lakhs of data or tens of lakhs of data, crores of data, so then GPU comes into play because it has this massive raw power, massive number of cores with a small control cache. So just one instruction and it will run that instruction on massive amount of the data. Okay, so let's take a look here. So this is the thing. So this CPU and GPU. So CPU is known as the latency oriented approach, wherein it just executes one program and tries to minimize the latency for running that program. GPU is throughput oriented program. So how you can just imagine this thing is, so CPU just minimizes the time to perform a single task. Okay, so for a single task is it tries to minimize the time, how fast you can run a single task, like as soon as possible, finish the single task as soon as possible. Okay, and the GPU is maximize the number of tasks that can be performed in a given time frame. So throughput is number of tasks given some time. Okay, so number of tasks per second. So GPU tries to optimize that I will do many number of tasks in each second. Okay, so it might not run one single task as fast as possible, but it will run massive amount of tasks within a given time frame. Okay, so arithmetic logic units where exactly the computation happens, for example addition, subtraction, or multiplication kind of thing. So they have very few but powerful arithmetic logic units. They have small, heavily pipelined. Okay, so the thing is, you can pipeline those ALUs. For example, if you have some dependent tasks, okay, so you can run just first part of this, then you can pipeline it with the next one, then you can pipeline it with the third one. So this sort of things you can do. And cache, so it has larger caches to convert long latency memory access into short latency cache access. Okay, so as I've uh, told you, right, so it maintains a hierarchy of caches, due to which the memory access is quite less there. Okay, like from the RAM it's quite less, and it fetches mostly from the L1 cache, L2 cache, or L3 cache, which are the faster sort of thing. Okay, they have high bandwidth and the access of data is pretty much fast there. But and here in the GPU they have small cache to allocate more area to the computation cores. And here if you see the branch control, so CPU has sophisticated branch control for the branch prediction and all, but it has very simple ones, and it leaves room more for the computation cores. Clock frequency for the CPU it's very high, and for GPU it's like not that high but a moderate kind of thing, but it is optimized for massive parallelism, like it can handle massively large data. And here wherein the GPU wins is the multi-threading. So CPU it's a modest multi-threading, for example 2 threads per core. And how the 2 threads are, for example if you are running a program, multi-threading kind of thing inside a GPU. So if one thread goes for the IO operation, the next thread can execute on the core. Okay, so they don't allow the core to sit idle. Okay, so that's how you can have maximum 2 3 like threads per core. But here it's a massive multi-threading with thousands of thread. Okay, with thousands of thread runs parallelly on a GPU to hide high memory latencies as well. Because say for example if you are taking much time to take the data from the DRAM of the GPU, but since you will use multi-threading, so all the latencies will hide, okay, inside this raw computation power. So here there is one short thing which I just need to address. Okay, so here why you think the GPUs are perfect for the graphics. So here you see, so the GPU renders graphic quite well compared to CPU. And here why? The thing is because CPU is a latency oriented approach. What CPU tends to do is it tends to render one pixel, okay, one pixel as fast as possible. So it just focuses on one pixel, running that pixel as fast as possible. But what about the GPU? It renders all pixels because it has this thousands of cores. Okay, so it renders all pixels within a given time frame. Okay, so how it works, so it's a basic thing. For graphics we normally use matrices. Okay, so matrix multiplication is what the graphics are for. So matrix multiplication is well suited for the GPUs. Okay, because say in terms of the images or the videos we have one 1080 megapixel kind of thing. Okay, so the pixels are in like lakhs of numbers. So if so what CPU does basically, it optimizes one pixel, then goes to another pixel, then goes to another pixel. So due to the large number of pixels, so the CPU becomes slow. But GPU, it handles all the pixels simultaneously at once. So say if a CPU can execute one pixel in zero point 0.1 second, CPU will execute one pixel in zero point 0.3 second, thrice, like it will take thrice time more. But within this 0.3 second it might have processed all the 1000 pixels or 1 lakh pixels. Okay, so that's how GPU makes it fast for the graphics. And here so the next thing is, so till here anyone have any doubts, or we will take the questions later, how is it?
I think we can take all the questions in the end.
Okay, sure. Okay then. Yeah, so the next slide talks about how the AI systems are built using the CPU host and the GPU device. As I said, like GPU alone cannot be used for building the entire AI system, because the GPU is not very good at the program counter, maintaining the program counter, the control cache or the instruction cache, how to give the instruction, then fetch the data, those kind of thing, because it is massively designed for the computation. Okay, so here we need to have some sort of GPU and CPU setting. So here if you see CPU, so CPU acts as a host, it controls everything, so acts as a brain that manages the overall artificial intelligence program. So what it does, it loads the data, it set up the models, and it sends the task to GPU. For example, I will start running the code from line number 1 to line number 2, line number 3, line number 4. CPU does all of that. And line number 5, if it has a massive matrix multiplication, so what it will do, it will dispatch it will dispatch the instruction to GPU, tell him to do the matrix multiplication and fetch the result from there, and then again start the execution. So this is called as synchronized execution, wherein CPU waits for the GPU to finish the sort of thing and take the output and then run the further program. So this is a synchronous scenario. But you can do also but you can do this thing asynchronously as well, wherein you give the instruction to GPU and start your own execution on the CPU. And when GPU output is available, you can just fetch the output and then continue the execution from there. So there are two modes of execution: synchronized, like synchronous or asynchronous. But as of now, we can just think of synchronous execution only. So it is good at general purpose task, but but not at doing massively parallel math. Okay, and this is where GPU comes into play. So GPU does the heavy math. Okay, so the GPU is just like a super calculator made of thousands of small computing arithmetic logic units. It performs the actual number crunching, like matrix multiplication in deep learning. So that's why if you are into deep learning, or if you are building models into deep learning, right? So when training the model, you will see when you train the model on CPU, it's much slower. Okay, it's much slower than training the model on GPU. And this CPU and GPU are connected via PCI bus. So the PCI is the high bandwidth bus which connects the CPU and the GPU, and the data transfers are done from this bus only. Okay, so the CPU sends data like the training images and the model parameters to the GPU, and after computation, GPU sends the result back to CPU using this PCI bus. And each one has their own DRAM. Okay, so both CPU and GPU have the same DRAM. So you might now relate to it, right? When you write this PyTorch code and you do this x.2 device, so what you do exactly is you transfer the memory of x from CPU to the CUDA device, which is the GPU. So that's where you need to do, because GPU cannot access the memory of the CPU. Even if you have a data on CPU, you need to copy it to GPU. GPU can run its computation, access its own RAM, run the computation, and send the result back to you via this PCI bus. This is how things work. And AI training loop happens here. So what happens exactly is CPU prepares the data, sends to GPU. GPU computes the forward and the backward pass, and the results go back to CPU for logging or the update. So this cycle continues. Okay, and this is the slide. I love this slide. So this is who invented this, the Linux operating system, and this was his thing. So talk is cheap, show me the code. So we'll go just to the code and see what all things we have learned. Can we apply it there, and can we see the speed up from CPU to GPU in comparison? Okay, so here I will do this simple program of vector addition. We'll compare CPU, which is written in NumPy, with versus versus the GPU program, which is written in Triton, and we will vary the array sizes from 1 million to 20, and then we will just see how the timing looks like there. Okay, so yes, so this is the demo. I'll just walk you through the code once. So yeah, guys, can you just see the code, or I'll just zoom in?
Yes, it is visible.
It is visible, right? Okay.
Yes.
Yes, so it's a simple thing what I'm doing here. So this is NumPy addition. So what we will do, we'll just create one random input. Okay, so np.random.rand, and we will pass the sizes. So n will range from 1M to 20M. Okay, like 10 lakhs to 20. Okay, 1M to 20M, we'll just pass it here, and then we will do this warm up step. Why we do warm up is because initially, like my CPU is not working right now for this program, and it just takes a bit to just start it and load the data and all of those things. So we'll just do a warm up setting wherein we will just add the vectors, like two vectors a plus b, and then what we will do, we will run, um, like we'll actually do the timing setting. So time.perf counter we will check, and then when the vector addition is done, we will again check the time, and then we will check what's the mean time, min time, and the max time of it. Okay, and then yeah, so I guess the code is clear. It's a very simple thing, and just let's try to run it once. So I will be connecting the GPU because I need to run this Triton code as well. Just a second, just a second. It will just take few minutes. Okay, it's connected, and let's run this code. Okay, nice. So you see, as the number of sizes increases, right, from 1 million to 20, the median time also increases. Okay, so this is 0.014, 0.2, and then 0.7. So, and here, this is the vector addition code written for GPU specifically. Okay, I'll just walk you through it again and how it looks like. So, many of you guys might not know Triton because it is not there in the academia yet. This is very internal details of the PyTorch, how you write kernels which runs on the GPU. But yeah, I'll just give you a brief introduction to it. Okay, so here you write this vector add kernel. You have this a pointer, b pointer, c pointer, which is a and b are the input pointers and c is the output pointer. Then you have this n is the actual number of elements, and then you have a block size. What the block size is, so if you see this CUDA programming thing, right? So what happens, we have a hierarchy. Okay, we have a hierarchy of thread block, thread clusters. I guess I can show it to you here. Thread blocks in CUDA. Okay, in CUDA, let me know if that is visible. I'll just take this thing. It's very nice documentation from them. Yes, here. Yeah, this thing. Let me know if this screen is visible to you guys. Okay, yeah. Let me know if that is visible to you.
Yes, it is visible.
It's visible, right? So as I told you, right, so GPU has massive number of cores, and each core can run one thread. Okay, so this is one thread, okay, per thread. And then what you do, you collect those threads into a block of threads. Okay, so a collection of thread is called a block, and then collection of block is called as cluster, and then collection of cluster is called a grid. So now you will ask why we need to block this or block certain number of threads into. So what happens is, when you block a certain number of threads inside a thread block, you can do the synchronization in a better way. For example, if your one thread is executing a statement and rest of the threads, like if one thread has completed the execution and rest of the threads are still completing, so instead this one thread going to execute some another program, you can synchronize. Okay, you can put a barrier or a fence inside a block wherein all the threads will come at this fence once, and then from there it can execute, and it can start the execution of some other program. Okay, so inside a block you can do various sort of things. You can do synchronization in a better way. You have shared locations where you can access data very faster. So this kind of things you can do inside a block, so that's where simultaneously. So this is a setting. Okay, so this is a brief overview of it. I won't go into the depth much because this is the very first session on it, and yeah, so things will get complicated. Yeah, so just coming back here. So this is how the block thing is there. Okay, so the block, you can just think of it as the number of threads inside a block. Okay, so this is one single block, and there you can do various sort of sophisticated things like you can do synchronization, you can access faster block spaces and all of those things. Okay, so this PID is program ID. It also represents the block number. You know, you can say it as, okay, the block number. For example, your say your block size is 1024. Okay, if your block size is 1024, so the block start will be, if it is a first block, so 0 into 1024, which is 0. So the start of the first block will be 0. And say your PID means the block number. I'll just write it here. So say block, if your block number is 1, okay, if your block number is 1, then what will happen is, this will be 1 into 1024. So the your second block will start from 1024. So this is how it is designed. And then you have offsets wherein you can access the thread numbers, and then you can load the data. So you load the data from a pointer, like this is the input pointer, data in the GPU. Okay, all of those things is like this all things, and then you will do C is equal to A plus B. The addition of two vectors inside the GPU, and then you will do C is equal to A plus B, the addition of two vectors inside the GPU, and then you will load, and then you will store the data, the result C, into the C pointer, which is the on the CPU block, because you need to print the data as well. Okay, and this is how so this is how you write the kernel. So this is known as kernel, the GPU kernel, which is responsible for the computation. And how you launch that kernel, you write it here. So this is kind of a kernel launch. Okay, I'll just go through it once. So this is C is, you just create one output pointer which is same like the A, because the input and output shapes are the same. If A is a vector, B is a vector, the C output vector will be of the same size as A and B. So that's where we used empty like. And then you define the grid. Grid, I use it to define certain parameters, like how many thread blocks will be there, and inside one block how many threads will be there. So this is how you define a grid. So we define a grid here, and then we launch. So this is called as kernel launch. Okay, kernel launch. So this is how you launch the kernel. You pass all the input and the output, and then you do torch.cuda.synchronize. So what will happen, all the threads will come here and wait. And then, so this is a warm up setting. Since we did warm up on CPU, so this is also a warm up on the GPU. And then we will use the time run. So we'll again have this perf counter. We will start, we'll do the vector addition, then we will wait for all the threads to complete the execution with torch.cuda.synchronize. Then we will do the end thing. Okay, like this end timing. if if I skip this, okay, if I skip this line, so what will happen, CPU will dispatch this instruction to the GPU and will start executing the next line. Okay, so while this program or this kernel is been running at the CPU will start execution of this line, end the time, and it will return you time, which is a garbage time. Okay, it's a wake time. So that's where we need the synchronous uh, information between the CPU and the GPU. So that's where we use this to torch.cuda.synchronize. So CPU will wait until you get the data from the GPU, and then we will just print the numbers. So again, the size is the same, 1M to 20M. Okay, and then yeah, so this is how the code looks like. And just we'll run the code and see the timings of it. Yes, yeah. So here we have the timings. So if you see, for the smaller ones, okay, so I'll just copy and paste it here. Copy, and then here just take a new thing. So this one is yeah, so this one is the CPU, clear output. Yeah, and this one is the Triton. Okay, so you see, for the smaller size, okay, for 1M size, the difference is not that big. It is 0.0001, it is 0.0006. Okay, so difference is not that big. But see, as the number of elements increases from 1M to 20M, as I've told you, right, CPU goes one element by one element, but here GPU will process entire 20 at once. So here if you see, there is a massive difference. Okay, so here for 20M, CPU takes 0.07, which is 7 into 10 to the power minus 2. But here the GPU takes 0.001, which is 1 into 10 to the power minus 3. Okay, so 7 into 10 to the power minus 2 to 1 into 10 to the power minus 3. So this is the speed up which I was talking about you get when you run this massive computation program from CPU to the GPU. Okay, we can just stop for a minute or two if you need, and then we will go to PyTorch and see how hardware aware information is impacting your AI models. Or yeah, if if you want it, or we can start it right away.
Yeah, I think we can continue with the session.
Okay, we can continue it. Okay, sure.
Yes.
So here, so yeah, we just looked at the demo, and yeah, so the talk was not all that cheap. So the talk was proved from the demo which we have done it right now. So the GPU is very good at performing the raw computation thing, in like with respect to the CPUs. Okay, so this was so this the first half of the lecture was just to make you understand why different types of hardware is there, and why different types of hardware are important for your program to run. And now we will see how PyTorch is the most loved machine learning framework out there. Like many of the researchers are using PyTorch as like to write code of their models. Hugging Face use PyTorch a lot. So PyTorch is the de facto standard. Like TensorFlow is also there, but PyTorch is the most loved one in the ML community. And how PyTorch realized this information that we also need hardware aware knowledge to make our program run faster. And that's where in March 2023 they came up with this PyTorch 2.0 stack, which has the compilation mode. Okay, so compilation mode and eager mode, I'll just tell you a bit about it when we go to the slide. You can think of it as a same difference between Python and C, which is ahead of time compiler which versus the interpreter kind of thing. Okay, so yeah, let's start with the PyTorch. Okay, so harnessing hardware-aware information intelligence for the performance. So PyTorch also uses that. And if I just show you how PyTorch exactly looks like, some of you guys who have taken ML as your specialization course might have used that or might have run that when you build model using PyTorch. So this is how it looks like. It's just a second, it will load. Yeah, so it's getting loaded. Till then, I'll just tell you a bit about the PyTorch. So PyTorch is right now the dominating framework in deep learning. Okay, so it is powering somewhere around 70% of the recent AI research implementation of 2024 to 2025. Okay, and over 63% of AI training models are built on PyTorch. Why? Because Python like PyTorch has this intuitive Pythonic interface. Okay, so PyTorch popularity is driven by its dynamic computation graph and intuitive Pythonic interface. So just the way you write your Python code, you can write the PyTorch code. Obviously you have to use some of the torch operations, torch.add, torch.nn, some sort of that thing, but the overall Pythonic structure is the same, like the def keywords and how you indent your program and then write your program, and then like classes, objects. Okay, so all of those things are very similar to Python. And it is also backed by Meta and supported by this PyTorch Foundation. So major companies like Tesla, Microsoft, Airbnb, and top research groups uses PyTorch for the applications. Okay, and just let's see. Yeah, so this is the PyTorch basic, and yeah, you can just go through it how the models are being built. So I'll just tell you a brief about it here. So this is how you define the class. So similar, like it's very kind of similar, just the way you define classes in Python. It's just class, your name, and from where you are inheriting. Okay, so this is the inheritance syntax. So it inherits from nn dot module class, and then you define the init function. This super init is you initialize your parent class first, which is nn dot module, and then you define your own layer, stack of layers. For example, you might have learned about the feed forward uh, layer, which is MLP or multi-layer perceptron, or what we can call it as a deep neural network kind of a setting wherein you have some output nodes, classic this one linear layer. linear layer, and if you just look at images, yeah, so this sort of a thing, you have input and it is connected through weights, and then you have this output. Okay, so this is a simple MLP, which is also called as multi-layer perceptron. So yeah, this is how they build this. This is self dot flatten, and then you have linear and ReLU stack. So you do this linear, this is the input and this is the output. So the weight matrix will be of shape 28 cross 28 into 512, and then you have ReLU, which is an activation function you used on the top of the MLP. Because if so say in a deep neural network, right, why is it performing better? For example, this LLMs, chat GPT, they are performing better than the classic models, just like the linear regression, the logistics ones. Why is it performing better? Because it is a non-linear kind of a setting. Because if you just eliminate this activation function, the whole neural network collapses into a equation of a weighted equation of the activation function. So this is how it works. And activation function gives you this smooth curve, which is the non-linear. You can just differentiate the circular regions from the non-circular ones. So like all of the sophisticated things, you can do it here. And then you have this forward function. So forward function is when you pass this x input to the model, what your output should be. So here you pass the x to the self dot linear ReLU stack, which is this model, and then it gives you the logits, which is the output of the model. Okay, so this is how you define a model, classic model. This is the PyTorch setting. And yeah, I've shown you why PyTorch is mostly used in this domain. Okay, and then you have two modes. Okay, if it is going to be very like if the talk is very deep, just take a brief uh, overview of it, which is eager mode versus compile mode. So the basic difference is the difference you see between the Python and the C or the C++. Okay, this is a compiled language, this is an interpreted language. And interpreted language, you have your numerous benefits, which is easy debugging kind of a thing. And it has an interpreter, so you just write a code, you don't have to compile it, just run it once, and just run it. Okay, so Python is not exactly interpreted but a hybrid language kind of. It has an intermediate representation bytecode which runs line by line. And C++, it's a compiled language wherein you take your entire program, compile it beforehand, and then you can just run the executable file. Okay, so what's the differences there, and why C and C++ is much more faster than Python? Is because when you know this entire information beforehand, you can do all sorts of optimization on it. The standard compiler optimizations, for example, dead code elimination, common sub expression elimination, all sorts of compiler things you can apply it there and make your like the entire program run as fast as possible. So yeah, so this is how the basic comparison is. So PyTorch mode, one is eager mode. So how it works, it runs each operation immediately as you write Python code. Okay, so the operation are executed step by step. Okay, one step, another step, another step, another step. For example, here which I have shown you here, example, if you run it in an eager mode, so it will run first this nn.linear, then it will like fetch the data, run this thing, and give the output back to CPU. Then it will run nn.relu, then give the output back to CPU, fetch the data from CPU, run this second 512 cross 512, return the data to the CPU, then again fetch the data from CPU, run this second nn.relu, and give the data to CPU. So this is how it runs, one operation step by step. Okay, the eager mode. So you can use loops here, you can use if else conditions here, every sort of things you can use. Okay, and the overhead is each operation involve Python interpreter overhead and extra kernel launches. Okay, which slows down large language models because you launch multiple kernels. You will first launch linear kernel, right? And then the data will be sent back to CPU. Then again you will launch nn.relu, then the data will get back to CPU. Again you will launch nn.linear, nn.relu, so one by one. So there is so many kernel launches, which is an extra overhead, and also the data accesses and all. But it is very good for experimentation, debug, model logic, the research and learning. So many of the research community folks, right, who are just writing papers and working on a problem statement. So they use this mode of a PyTorch because it is very easy to implement a model in this way, because they don't care much about the performance. That is like that work is up to the ML engineers working for the companies to optimize the model on their hardware. So there is so these guys, okay, which are the data scientists and all, they just focus more on solving the problem, improving the accuracy and those kind of things. So PyTorch gives you this mode, which is very used for the research community purposes. Okay, so this is how things work. You have torch.nn, just the way as we have seen, it internally calls the Python API, and then Python API and the PyTorch, they are all like beneath that, it is all written in C++. Okay, so this autograd is written in C++, A10 operation, just in time compilation, it's written in C++, and in the meantime it just calls the CUDA kernel if it wants to run in GPU, and if it wants to run in CPU, it will just call this C kernel. So this TH, okay, so the TH stand for torch. So the first T and the last H, okay, so TORCH. So yeah, so this stands for torch. So this is how the eager mode is. Compile mode is very different. Compile mode is like it builds and optimizes a computational graph from your model. This merges many operation into fewer and faster kernel before running them. Okay, so here I'll just give you a brief overview how it happens. If I go back to the model, so what will happen is the compile in the compile mode, this class of neural network will get called, and then what it will do is it will create a graph. Okay, it will create a graph. For example, one node is the linear node, then the data goes to the ReLU node, and then the data goes to the linear node, and then the data goes to the ReLU node, some sort of a flow chart. Okay, flow chart you can think of it as. Okay, so it will create a graph, and then it will think what all things we can merge. For example, linear and ReLU, if we can merge, so how the performance will improve is I will need to fetch the data. Okay, so here previously I will have to fetch the data. For example, I'll just write a quick example here in Notepad. So say if you have this thing, okay, linear, just a second, it might not be visible much. Okay, so linear, then ReLU, then linear, and then ReLU. Okay, so here in eager mode, what will happen, here you will have um, like two CPU calls, one to fetch and one to load the data. So two CPU call. Okay, so one will fetch the data, run this thing in a GPU, and will give the output to CPU. So two CPU calls. Here again you will have this two CPU calls, and here also you will have two CPU call, two CPU calls. So total you will have eight CPU calls and memory accesses. Okay, eight CPU calls and memory accesses. But if you just combine some of the operation, for example, if I combine this linear plus ReLU, and if I combine this thing linear plus ReLU, so what will happen, I will fetch the data, I will fetch the data once from the CPU, run these two things together, and then output it to CPU. So this whole block will require just the two CPU access, and similarly this whole block will require just the two CPU access. Okay, two CPU access. So we have reduced the CPU calls from 8 to 4 CPU calls, and the memory access have also been reduced, right, somewhere around a 50%. And you will ask how we can merge. Okay, so there is this thing, very sophisticated kind of thing to write the kernels, because many of the guys are very much into the kernel writing. They know how to fuse the mathematics of two and write just one simple formula. For example, if you have simply like, I will give a simple example for you to imagine. For example, if you had two components, which is multiplication, which is say x plus 2 or x plus 1, and then you have addition, which is x plus 5. Okay, and this will be x into 5, some sort of that. Okay, so here what will happen, first mul will get called. It will fetch a data from CPU. Okay, it will fetch a data from CPU, do x into 5, and give the data back to the CPU. So two CPU call here, two CPU call here, two CPU call here. But if I write a very sophisticated kernel inside a GPU which can do mul and add simultaneously, mul add simultaneously. So how the equation will look like is x into 5. First you do x into 5, then don't send the data to GPU, you just add 5 to it, and finally send the data to CPU. So here you see we can fuse multiple kernel into one. Okay, this is very simple thing. um, this thing anyway get fuses inside the PyTorch mul and add, but there are many things. Okay, just the like convolution batch norm, they get fused into one kernel. So what this does is this reduces the number of memory accesses and the CPU call, and in turn it optimizes the performance of the model, and the model runs very fast on the GPU in that setting. Okay, so so the compile mode, how it works, it captures a graph, it sees what sort of optimization I can done on the graph. For example, if there is any dead code where the graph is not reachable and the branch is there, it removes that branch. And if you have common sub expression, for example you are using 5 plus 2 there, 5 plus 2 there, so it will just remove this 5 plus 2 and insert 7 there. Okay, so this sort of things it does. All the standard compiler optimizations, it does the fusion. Okay, so it merges many operation into fewer and faster kernels before running them. So this is how you improve the performance of the model. And this is the PyTorch 2.0 backend. The front end is Dynamo and AOT Autograd, and the backend is Inductor and Triton. Triton is, if you remember, we wrote a program in Triton to run it on GPU, right? So PyTorch internally uses Triton to generate the code to run on the GPUs. Okay, so this is how things are. And now for you guys, I have just taken this kind of a thing, this kind of a Triton code. So what I did, I have created a model which was class MLP, and then this super.init, then I have written this forward function, and then I have captured the log. So this torch.inductor gives you this Triton code as output. And here I just want you to just connect that information, the Triton information, to this, that yes, whenever the PyTorch wants to run its code on the GPU, so this is how it runs the code on the GPU. It internally creates this number of Triton kernels, number of Triton functions, and then this Triton functions runs on the GPU. Okay, so this is the thing. And again, like, all the talk is cheap if we don't look at the code. And yeah, so right now just we'll take a look at the code itself. So here I'll just reconnect it. Yeah. So here we have written this MLP, which is very small. We have just called the pre-trained one. And here, if you see, so the device is CUDA because I have taken this T4 GPU. Okay. So the device is CUDA. I have a GPU. I will take a model which is ResNet 101. Okay. This ResNet is a model which is based on the convolutions. Okay. So I will take the model, and then I will run dummy input. Okay, so the dummy input is, I will just use this model which is the eager mode. Okay, I will run it on eager mode, capture the performance, then I will explicitly call torch.compile. What it will do, it will run the model in a compiled mode. It will make a graph of the model, fuse certain operations to like to reduce the number of accesses, and then we will run it. Like, I will run this model 80 times, and again I will run this model, the compiled one, also 80 times, and then I will just take a look at what was the eager time, how much time it took for running in the eager mode, how much time it took running it in a compile mode, and eager mode versus the compile mode speed up. So now you will ask how the hardware aware information. So this is where the hardware aware information comes into play, because if you know about the hardware, you can generate the Triton kernel which exploits your hardware in a very much efficient way. For example, this thing, okay, size is 4096. You have this again X block. Okay, this block size. And I have told you earlier, this NVIDIA GPUs, right, they operate on the concept of block size. So for certain program you might use a block size of 1024, but for certain program you might use a block size of 1024, but for certain other program you might use a block size of 512. Okay, so this is where hardware aware information comes into play. If you use certain block size which are very optimized for your hardware, your program will run way faster. And why? and why we need to think of hardware, and why we need to run the model again and again, because the training is done only once, but the inference is done millions of times. For example, you guys might be using chat gpt in your daily life, like within a day you might be using it 10 to 4 times. Okay, so if you are using 10 to 4 times, there are crores of people using the chat gpt 10 to 4 times. So these many prompts are there, these many number of instances they need to run, these many times they need to run the model repeatedly on the hardware. So that is why we need very efficient model. So if you don't run your model efficiently, you won't get the answers in time, you will get just a word by word by word output, you will get bored looking at it. So this is how things work. And yeah, just take a look at the demo once. So I'll just run this code here. And yeah, it will take some time because I'm running this eager mode. 80 times I will run in the compile mode, and I have again included this warm up step just to stabilize the hardwares. Yeah, so it is downloading this pytorch model. Okay, then till the model is running, we'll just take a brief introduction to this AI accelerators. Okay, and just so till now we have learned about this CPU and the GPUs. We haven't touched this AI accelerator much. I'll just give you a brief introduction because anyhow this is like very daunting to learn more about the hardware. But yeah, what are accelerator? I will just give you a brief introduction. So if you see, that's a line which is the general purpose programmability, which you can program very easily. And then you have this efficiency. Okay, so these two are very separated. CPU and GPU lies here, which is general purpose and a bit efficient, and you can program those things very easily. And this AI accelerator, which are FPGA or ASICs, okay, application. So ASIC stands for application specific integrated circuit. So that integrated circuit is designed for just one single application. Okay, so just imagine if you are hardwiring it, okay, if you are hardwiring it for doing certain computation, how fast it would be. Because computation on hardware is really fast, like compared to the software, because anyhow you have to run it on the hardware, right? So these ASICs are way faster, but it is very hard to program those ASICs because you need to go to the intrinsics level. You need this assembly kind of instructions to program this ASIC. Okay, so here this CPU GPU is there, and you also have this AI accelerators, which are TPU, Intel's Gaudi, and then Qualcomm's AI 100 accelerator. Okay, so this the design goal here is general purpose computing, which is branching, OS, and all of those things. GPU is designed for highly parallel compute, massively, like massive number of cores. And AI accelerator, they are specifically designed for machine learning acceleration, machine learning operation. For example, they have this specialized MMA engines, which is known as matrix multiply and accumulate. So they do multiplication and add at the same time. Okay, so their circuit is designed in such a way. They have this MMA engines. So cores, CPU has few cores, GPU has thousands of cores, and here you have hundreds of thousands of cores. Again, this matrix engine which I was talking about, this MMA engines they have. And precision, so they work on FP60 to FP32. GPU, it runs on floating point 32, floating point 16 bits as well, and BF16. Okay, so here for 16 you have 16 bits, one sign bit, and some 5 to 6 exponent bit, and rest is the mantissa bits. And you have B float 16, which also takes 16 bits, but here the exponent range is much larger compared to FP16. And the accelerators, they run on very low precision mode. For example, int but 8 bit. Okay, so 8 bit integers, BF16, FP but 8 bits. Okay, and then programming. So here it is very easy to program like CPU. Okay, and it is very easy to program GPU as well. You have CUDA, you have Triton, you have OpenCL. But here for accelerators, right, you need to have certain of the intrinsics like Synapse AI, SDKs. These are very much specific to the company, very proprietary to the company. Okay, and power efficiency, so this is low power. GPU is better throughput per watt, and it is highest throughput per watt. So GPU, so you might have read that sentence when Sam Altman said, when this trend occurred, right? The this one Ghibli Studio images, some sort of that trend. So Sam Altman tweeted that our GPUs are melting because GPU requires very high power. Okay, it runs the compute, but it requires very high power. It it needs specific data center, AC cooled, and those things. But the accelerators, they are very highly optimized per watt because they have this circuit doing most things for them, and it is best suited for control heavy tasks, which is the data pre-processing and all. GPU, as we have seen, it is very compute heavy for graphic workloads, for ML workloads. And this AI accelerator, these are very specific to just AI workloads, not the graphic ones, just the AI workloads. Okay. And now let's see whether our program has run. Yeah. So here you see. So eager mode took 3.5 seconds. Okay, and compile mode took 2.9 seconds. So we have a speed up of 1.2x. Okay, so here it was a comparatively smaller model compared to large language models, because here you see the size of the entire model is 171 MB. But if you like go to the large LLMs, okay, it is of a GB kind of like parameters and the size of the model, wherein you can get some significant speed up to 3x 4x speed up. Okay, but here since since it is a compile mode and there is this graph fusion and ahead of time compilation, so we have seen this kind of a speed up in the compile mode. Yeah guys, so again, thank you so much for your hardware. It is very performant, it can give you way more performance than anything else. And if you're curious, you can explore this Triton thing, and you can explore GPU programming or hardware acceleration. So that's where the next AI innovation is there, because you might have seen in the stock markets as well. So semiconductor is in boom right now. This Nvidia, AMD, all of those stocks are just rallying. So they have this immense need of the semiconductor, immense need of the GPUs, immense need of the accelerator. So this is where you will so if you explore much, you can have a better job opportunity or better job aspect there. And if you need, you can connect me here, you can connect me on LinkedIn, you can connect with me on the Gmail itself. I end this session, and any questions now?
Thank you so much for your insights, sir. That was really wonderful to see how we can use CPUs and GPUs, what is
Yeah.
the difference between them, and why hardware, looking at hardware is
Mm,
important as a software engineer.
yeah.
So I'll just take up some questions that we have in the chat box,
Yes.
and you can answer them one by one. So if you could go back to your college days, what are
Mm.
some things you would do differently to prepare for your current role?
Okay, so if I go back to my college days, I would focus more on this any framework. So if you feel like you are interested in TensorFlow, I might took TensorFlow. If I was interested in PyTorch, so I would take PyTorch and I would explore the intrinsics of the PyTorch. For example, how to build a model using PyTorch and run it, and again how to optimize this model for running better on a GPU. So this kind of thing I will explore more, because this kind of job opportunities are there. And yeah, I've seen many companies hiring ML engineers for the same. So to give you a brief overview, so you have data scientists, you have ML engineers, you have ML ops. So ML engineers come like as a blend of software engineer and ML as well, where you just try to make systems more suitable for your hardware. So if I go back to my college days, I would focus more on writing PyTorch code and running it more efficiently on GPU, and do this Kaggle competitions more. So there is a Kaggle website wherein you can just submit your models and get onto the top, and then just boast about it on my resume and get hired.
Yeah, that's really nice.
Mm,
So another question that has come up is what inspired you to research in the hardware domain when
mm.
people generally choose the traditional software path?
Yeah, so the thing is, when I like during 2020, right? So there was this artificial intelligence boom, and there was more like you can do many things. Okay, you can automate many things. For example, scripting is very much gone right now, wherein you write script for test automations because these things like the Chat GPT or LLMs can write it in one shot. Okay, so those things or very generic things. For example, if if you build a sophisticated web development, then it's fine. But if you are just stuck on to html css and javascript, still it's a way danger zone because like chat gpts can do it like very quickly. So I was of that thing like I was since the very start because Indu ma'am was there when I was in my college days. She took our DSP's lectures, and we also had this microprocessor and microcontrollers lecture. I was interested in that, and I thought to explore that a bit more, but in the ML domain because that's where the trend was. Like larger and larger models were there, so that's what fascinated me to go to towards that domain.
Okay, that's interesting.
Yeah.
So for a student who is currently in their third year or final year,
Yeah.
and they have listened to your talk and they want to explore more
Yeah.
in this domain and follow the path that you have
Yeah.
followed, what advice would you give to them?
So I will give them this advice of explore PyTorch as much as possible, and just the way like for the students who are interested in C++, they attend this C++ conferences. So you can attend PyTorch conference, which is happening very recently right now, and they have this. YouTube playlist PyTorch, okay, so they just published conferences there, talks, okay, so you can attend those PyTorch conferences and Triton conferences to see where the community is going towards. Okay, because as I have said, we cannot run a single model on a single gpu right now because the transformer size are huge. So how distributed learning are into place, how you parallelize the model, how you parallelize such, and they will also talk about how you handle such humongous traffic. Okay, because as I said, crores of peoples are using chat gpt, so many requests are there, how you are managing those traffic and running the model efficiently there. Yeah, so just start with pytorch conferences, triton conferences, and try to build models, because until you get your hands dirty on writing models or writing code, you will have the fear of writing the models and training it from scratch. So you have to get out of that zone.
So previously you have also worked at Intel and Qualcomm.
Yeah.
So if students want to go to those companies after graduation or work on internships over there, how can they approach that?
Yeah, so for approaching, firstly, there are certain prerequisites, which is you need to be very much comfortable with C++. And why C++, I'll tell you. So while mentioning that PyTorch stack, right, I showed you that internally it uses C++ calls. Because when you go to the hardware level, right, it's all about the faster things. Okay, so C and C++ are there. So just get comfortable with C++, get comfortable with PyTorch, and the Kaggle board is important. If you show yourself that you can write great models in pytorch, and you can use the training data efficiently, and you are top of the board, so if you write it in your resume, because while conducting interviews for those companies as well, right, I was conducting interviews for those companies, so they focus more on how like how minimal training you required when you join the company. Okay, so it's more like you should know ml beforehand, you should be comfortable with c++, you should know how to build models, and you should know what optimizations are there. For example, this torch compile mode, you should know like how it optimizes the models and
So that's really helpful to anyone
all.
who's looking to work more
Mhm.
in this domain. So from your perspective, how is India evolving in the AI hardware space
Mhm.
compared to the global landscape?
Yeah, unfortunately as of now we don't have much. Okay, like our governments are spending. Okay, so they are incentivizing the semiconductor stream to work on that. But yeah, because you see, right, in fact it's more about the overall AI landscape and the hardware optimizations. It's just about this Intel, Nvidia, AMD, and all of those things, right? Yeah, so unfortunately not much here. Yeah, so you have to look outside. So outside landscapes are much more evolving because we have some great startups from there and China as well. So China has this DeepSeek, okay, so they came up with just amazing paper DeepSeek, which uses very less computation, and it is on par perform it is on par on performance with some of the frontier models, okay. So China and US, if I want to say, and UK as Europe as well in general, because they came with this Mistral and all. Yeah. So
Okay, so
yeah.
that's really helpful to know.
Mhm,
So thank you so much for
mhm,
taking your time and guiding us
mhm,
throughout this session. It was really, really nice to see how the internally
mhm,
CPU and GPU work. I would
mhm,
like to thank Dr. Indu Dokre and Priya RL ma'am for helping us conduct this session. Also, our HOD, Dr. Nupur Giri, and Deputy HOD, Dr. Gresha
mhm,
Bhatia, for
mhm,
guiding us throughout. And yeah, thank you to all our audience
mhm,
members for tuning in, listening to us.
mhm,
It was really wonderful to hear from you, and we are
mhm.
grateful to have you. Thank you, sir.
And thank you so much. Thank you so much, everyone, for conducting this. Thank you.